these are notes on phase change and heating curves. So we've already learned a lot about phase change and absorbing energy and releasing energy as that phase change happens. So now we're going to apply it to the heating curves that we made for water. All right, so here is basically the heating curve you should have gotten for water, with a couple of exceptions. So I started my heating curve below 0, and so that means I took the ice right out of the freezer and got its temperature right away before it kind of heated up a little, and so that's why mine was below 0. Because you started yours with water, like a little bit of liquid water in it, you weren't able to get it that cold. But what I can tell here is my curve kind of swoops up and then it stays stable for a little bit. Now yours may or may not have stayed as stable depending on how well you were stirring your water. And then it swoops way up, and then it stays stable at about 100 degrees. And I know in class, looking at everybody's data, yours probably stayed stable around 95 or 96 degrees, and that's okay. There's a couple of reasons that may have happened. But then if I were to collect the steam and that was bubbling out of the water, the liquid water, and I could keep heating that steam, I would expect that this could rise again. But it would only rise as it were a gas, not as liquid water. So let's put a few labels on this graph. So here is where the solid was melting into liquid. Up here is where the liquid was boiling into solid. So we've got some phase changes. We can also put in some states of matter. So the solid would be down here below where it melts. The liquid would be here between where it melts and where it boils. And the gas would be here after it has all boiled. Now, where do you think we would put condensing and freezing on this graph? Go ahead and pause the video and see if you can predict where condensing and freezing should go. So condensing would go right here, right? Because condensing is the opposite of boiling. So if this is the temperature where the liquid becomes the gas, then this must also be the temperature where the gas becomes the liquid. And the same for freezing. If this here is the temperature where the solid becomes a liquid, then this has also got to be where the liquid becomes a solid. So it's the exact same temperature. And just like density, where if you had something's density, you could figure out what the substance was. Remember, we said that's a characteristic property of matter. Melting point and boiling point are also characteristic properties of matter. So if you saw this curve and it didn't say it was the heating curve for water, but you knew that water melted at 0 degrees and froze at 100, you could tell that it's water. If you had a different curve, let's say one that went like this, that would be a different substance. We'd have to find a substance that melted at, say, 18 degrees and boiled at like 75 degrees. So that would be a different substance. One of the questions is, why doesn't the temperature increase during phase change or decrease during phase change? So we know, for example, up here, that we're still adding heat to the water. And here, when we're adding heat, the water continued to rise in temperature. But here, when we're adding heat, it stopped rising in temperature. But then it would start again if, as I said, we were able to collect the gas. So pause the video, think about where you think all that heat went. All right, so remember back to what we talked about, that boiling is an endothermic reaction. So it's taking heat to drive that reaction. It's absorbing heat. And then remember when we talked about how the particles, the water molecules, move between liquid and gas. During liquid, they're still touching each other. So there are bonds between them. When it's a gas, those particles, those molecules are no longer touching each other. So there's no more bonds. But there needs to be some energy in order to break those bonds, to run that endothermic reaction. So the energy you're putting in is going to break the bonds between the water molecules. If we suddenly stopped heating it, let's say we took the beaker off of the hot plate, it wouldn't continue to boil. The temperature would drop down and it would stay liquid. So that energy is going to break apart those molecules. Here, between solid and liquid, it's going to not break them apart, but break them, let's say break them a little bit apart because they're not touching as much as they are when they're solid. All right, so now let's look at a different graph. So these are called phase diagrams, and they relate pressure and temperature. So far, if we look here, we've only been talking about temperature. We've said things freeze at a certain temperature and things boil at a certain temperature. But pressure also has to do with it. Just like we can say the density of water is 1, but then we know if water is hot or cold, it's not going to be exactly 1, it's going to be more or less. Pressure also affects temperature. Pressure also affects phase. Some of you may have heard that, like, if you go into the mountains, like in Denver, where it's a mile above sea level, water is going to boil at a lower temperature. So that's the same thing as like density and temperature. Pressure and boiling point and freezing point, or pressure also affects boiling point and freezing point. So this is kind of a complicated graph. Let's look first just at this one for water, okay? So whenever you have a phase diagram, you're going to have 3 sections. So here's the solid section. This is where water is solid. Here's the liquid section. This is where water is liquid. And here's the vapor or gaseous section. So this is where water would be gas. And at 1 atmosphere, that is sea level. So we're about at 1 atmosphere where we are in Seattle. So this is the pressure side and this is the temperature side. So if you notice, this is 0 degrees Celsius and this is 100 degrees Celsius. So if we follow the 1 atmosphere over, it's solid until we get to this line where we notice now it's going to transition into liquid water, and that's at 0 degrees. If we continue to follow the line over, here at this line, this is where the liquid water will turn into gas at 100 degrees. I think I said 100 here. I meant 0 degrees here and 100 degrees here. Okay? Now, let's say, though, we are we're up in Denver. And in Denver, I don't know exactly what the pressure is, but it's less than it is here in Seattle. So if we follow this line over, notice we're going to get water boiling at a lower temperature. And that's because there's less pressure, and so there's less force actually holding the water together, and so it's easier for it to break its bonds and turn into gaseous water. Now this is a really interesting one, this phase diagram here. Same idea, and we see our same 3 categories. Here's our solid portion, here's our liquid portion, here's our vapor portion. But this is for carbon dioxide. Now remember, carbon dioxide is what we had in class. So here we've got 1 atmosphere. And notice at 1 atmosphere, so that's about where we are in Seattle, there's only 2 options if we follow this line the whole way over, solid and vapor, because the pressure is so low that, that there isn't a liquid state of matter at 1 atmosphere. All right, sorry about that, had to sneeze. Okay, so here at 1 atmosphere, we can see that the carbon dioxide goes straight from solid to gas. So that's that subliming, right? And we might think that then carbon dioxide doesn't exist as a liquid, but it's just that the pressure at 1 atmosphere is too low. If we were to increase the pressure, so let's find this is 0 degrees, right? So let's say like room temperature, okay? If we were to increase the pressure here, and I don't know where room temperature would be on this graph because it's clearly not to scale, but at some point up in here with a much higher pressure, we could get carbon dioxide to be a liquid. And if you think about like a 2-liter bottle of soda or any bottle of soda, before you open it, that carbon dioxide that's making the bubbles, the carbonation, is in liquid form. And it's in liquid form because they've pressurized the bottle. That's why when you go to open it, you hear that escape of gas because suddenly the pressure has dropped way down, and now that carbon dioxide exists as a vapor instead of a liquid. But carbon dioxide can be a liquid, you just need to make sure the pressure is high enough. So just like density, where yes, density is a characteristic property of matter, but it can be affected by temperature, melting and boiling points are also characteristic properties of matter, but they can also be affected by pressure. Please make sure you ask any questions you have so that this is really clear for you. Have a great day.